This is a continuation of section 4.4. Today we're going to look at some problems that are just a little bit different. They are the same type of problems where you still need to draw your picture, come up with your two equations, and solve for the variable indicated. We're looking at maximizing and minimizing volumes today. So our first example is from page 227. It is number 12. A 1,125 cubic foot open top rectangular tank with a square base X on a side and Y deep is to be built with its top flush to the ground to catch runoff water. So rectangular tank, so we're talking about a box. So if I draw my picture here, I got my box. Okay, this is X and this is X because it's a square base. And then Y is my height. The cost associated with the tank involved not only the material for the tank, but also an excavation charge proportional to the product XY. If the total cost is C equals 5 times X squared plus 4XY plus 10XY, what values of X and Y will minimize the cost? So we're trying to figure out is how cheaply can we build this tank. So first, we know, because this is given in feet cubed, that we're talking about volume. So the volume of our tank is equal to X times Y, which is X squared Y. We also know that our volume was 1,125, so our first formula is 1125 equals X squared Y. Alright, now easiest way to solve this guy would be to get Y by itself. So Y equals 1125 over X squared. Now our next formula is C. We can see C right here. I would recommend that we distribute the 5 and then combine like terms. So I'm going to end up with C equals 5x squared plus 20xy plus 10xy, which makes C equal to 5x squared plus 30xy. Alright, now I have my two formulas. If you recall from last time, we are going to take what we got for Y and come over here and plug it in for Y. So I end up with C equals 5x squared plus 30x times 1125 over X squared. I will go ahead and simplify right now. So my X and my squared are going to cancel out. Go ahead and multiply those two together. So I get C equals 5x squared plus 33750 over X. Now remember, we're looking to maximize or minimize our value here, so we're looking for the minimum amount of cost for the material needed to build this box. In order to find the minimum, that's one of our extremes, so we find the first derivative and set it equal to 0. So to find the first derivative, we are looking for C prime. For the first guy, very easy, 10x. Next guy, remember, is the same as 33750 x to the negative 1. So, I'm going to go ahead and do that. So, minus 33750 x to the negative 2 is my derivative. Let's set that equal to 0. So, 0 equals 10x minus 33750 over x squared. You get a couple options here. I would recommend finding a common denominator first. So in order to do that, x squared is our common denominator. So we're going to have 0 equals 10x cubed minus 33750. You can solve this guy for x cubed. So add your 3375 to the other side equals 10x cubed. Divide by 10. And then because I have x cubed, I'm going to take the cubed root of this, and I find out that x equals 15. So 15 is going to help minimize my value. Now the question asks what values of x and y will minimize this. So I know x equals 15. I'm going to go back to my volume problem. 1125 equals 15 squared times y. Divide by 15 squared. Y is going to equal 5 feet. And don't forget to label your values. So the minimum is going to happen when the base x is 15 and the height y is 5. That's going to give me the cheapest tank to produce. Alright, let's move on to the next example. In this example, we have a little picture here to help us understand what's going on. We have a piece of cardboard that measures 10 by 15. Two equal squares are removed from the corners of a 10-inch side as shown in the figure. And then two equal rectangles are removed from the other corners so that the tabs can be folded in to form a rectangular box with a lid. Okay? So you can see in the picture here. Now the question is, in this case, the question comes in two parts. Our first question is to find the volume. Find a formula for volume. So looking for the volume of the box. Now you'll notice that the height of my box is going to be x, because this distance and this distance are going to fold up, so they're going to talk to me about the height. So height equals x, width equals 10, which is my total distance here, minus this x and this x, so my width is 10 minus 2x, times my length. And length is the one that's going to be a little bit confusing here. So we find our length. We see the whole thing is 15. Okay. But I took out a piece here that's x and a piece here that's x. So our length is going to be 15 minus 2x. But it's also double because I have the base and the lid. So I have to cut that guy in half somehow. So I'm going to do divided by 2 for my length. So we know volume is length times width times height. So my volume is x times 10 minus 2x times 15 minus 2x over 2. Alright, go ahead and distribute this out. We're going to end up with 10x minus 2x squared times 15 minus 2x over 2. I get 150x minus 20x squared minus 30x squared plus 4x to the third, all divided by 2. And I can go ahead and combine my middle terms, but also because every coefficient here is even, I'm going to go ahead and divide those by 2 as well. So 150 divided by 2 is 75x. Here I have negative 20 and negative 30 is negative 50. Divided by 2 is negative 25 x squared, and 4 divided by 2 is 2 x cubed. And there is my formula for volume. Now the next question asks, what is the domain of this function? And so I have to understand, if it wants to know the domain, I need to understand my requirements for my length, width, and height. So part B to find the domain, I need to know what's going on here. Well, first, x, my height, has to be bigger than 0. I can't have nothing. I have to have a height. So x has to be greater than 0. Well, if x is greater than 0, then if I solve this guy, 2x has to be smaller than 10, because 10 is my maximum width, and I'm cutting parts off of it. And then my length, 15, has to have 2x less. So, if I solve these guys, I end up with x is less than 5, and x is less than 7.5. Well, if x has to be less than 5, it can't get all the way to 7.5, so this one doesn't matter. And it also has to be greater than 0. So my domain becomes 0 to 5. Alright. The third question that they ask us, part C, is where does the minimum occur on our domain? Alright. So they're asking us where the minimum occurs. We need to figure out, the maximum. Where's the maximum volume over our domain? So to find the maximum volume, we have two options. We can look at the graph, which we've done before, and we can find the first derivative and set it equal to 0. So we're going to change pages here. We know our volume equals 75x minus 25x squared plus 4x cubed. Well, v prime, 75 minus 50x plus 12x squared. If we want to pause. Alright, this should be 2x cubed. I miswrote it. So it is 6x squared for our v prime. Set that guy equal to 0. Now, when you go to set this equal to 0, it's not going to factor. Okay? Not going to factor. So, you got a couple of options. You can use quadratic formula. You can use the solving function on your calculator. When you do that, you're going to end up with x equals 1.961 and 6.371. So these are my two critical points. I need to know which one is happening, though, over my domain. So that's why the domain question was so important. We said our domain was from 0 to 5. So the only one that occurs from 0 to 5 is at 1.961. So 1.961 is my maximum height, or the maximum amount I can cut out of those corners in my picture. And then my maximum volume, if I take that height and I plug it back in up here for volume, my max volume at that point is 66.02. Okay. So, we went through two different examples today, asking some very different questions. Please make sure you go through your homework, page 227, and do 11 through 19, the odds this time. The evens in this section are also posted to eChalk, so if you want to see how some of the even questions were worked out, I would send you there. Thank you.